Hi everyone, thank you for visiting our VPCO presentation. Now you are hearing Kadek Hendrawan Palgunadi speaking. In this virtual EGU, we would like to present our study titled Cascading Earthquake on the Fracture Network in Geo-reservoir, co-authored by Alice Gabriel, Dmitry Garagash, and Martin Mai. Fluid injection into fracture network close to unmapped or mapped fault plane, as shown by this left panel figure, have been widely known as a source of significant induced event. And if the injection activity close to the populated city, it is prone to have a high seismic hazard. Our understanding currently of an induced event to dynamic slip on large unmapped or mapped fault plane is due to the perturbation to the fault strength that can be caused directly by elevated pore pressure change in fault loading conditions, and or stress transfer initially by a seismic slip from the stable part to unstable part of the fault plane. Now, what if a slip on the fault cannot be activated by the fluid injection due to poorly oriented fault plane with respect to the regional stress loading? Because there is a possibility for favorably oriented fracture network close to unfavorable fault plane that produces cascading rupture. One may ask questions: can favorably oriented fracture network host a cascading rupture? And then another possible question may arise: is it possible for dynamic stress interaction among fracture and activated the poorly oriented manifold plane and generate a bigger earthquake magnitude? Non-double couple moment tensor solution on induced events can indicate at least four possibilities. They are a tensile fracture growth, multiple intersecting fractures, dilatant jogs created at the overlapping areas of multiple fractures, and non-planar pre-existing fault. However, in this study, we are interested in the point number 2 and number 3, where the observed non-double couple moment tensor solution could represent a cascading rupture. The aim of this study is to answer two main questions. Is sustained cascading earthquake rupture possible in a fracture network? And do such cascading earthquakes require a rupture on the main fault or not? The semantic map view of how cascading earthquake can potentially occur on favorably fracture network can be seen from the figure on the right. The thick black line represent the main fault plane, and dense intersecting lines illustrate the fault damage zone, and then the thin lines here denote the fractures. Sigma 1 is horizontal maximum stress loading, and sigma 3 is the least horizontal stress loading. A fluid injected into this area, an increase in pore pressure shown by delta P will first activate a slip on favorably oriented or critically stressed fractures. This initially a stable slip may transition into a dynamic slip, promptly arrested at the fracture tip. And if a favorably oriented fracture are connected, it will attribute to a cascading rupture. The unfavorable manifold with respect to regional stress required larger pore pressure to activate its dynamic slip. And hence, to have a dynamic cascading rupture, there are prerequisite conditions, such as a fracture should be favorably oriented to the regional stress loading, and all fractures should considered as seismogenic on all scales to support co-seismic slip. In this study, we look at one configuration of regional stress loading, assuming fractures being favorably oriented and the manifold is poorly oriented. Therefore, we want to test three different possibilities of injection scenarios that translate fluid injection, or in this case represented as strength or stress perturbation, to generate cascading rupture. Scenario number one, where stress or strength perturbation along the main fault only, for example, injection directly into the fault core, assuming the vicinity of fault core is permeable. And then scenario number two, where the stress or strength perturbation into a rock volume spanning a subset fracture system within the fault damage zone. And finally, the scenario number three, that is similar to scenario number two, but with stronger stress perturbation. To construct the fault and fracture network model, we follow Savage and Brodsky 2011 to populate fracture density and length distribution as shown by the map view of the fracture network here. To populate the fracture orientation, we follow numerical experiments of off-fault fractures on damage zone that represent pairs of conjugate fractures near the main fault plane with the same evidence from field observation by Michel and Faulkner 2009. As shown by StereoNet, we populate fractures into two families with strike line to north 20 and north 120 with standard deviation of 10 degrees. We use industrial standard software fragment to generate the fracture network using nearest neighbor algorithm. The fracture radius size spans from 18 meters up to 2 kilometers. In this study, we consider the fracture plane to be elliptical instead of rectangle shapes. Then we use C-modeler software to generate the numerical tetrahedral mesh. The element mesh size is refined towards the fractures of fault plane as represented by a dense lines here. As a result, we have about 18 millions of tetrahedral mesh as shown by a crop view of the rendered mesh. Next, the output fracture plane from fragment after meshing is inserted into numerical software Sisal to simulate earthquake dynamics and seismic wave propagations. The 9-second simulation time requires approximately 15,000 cores on Shaheen 2. Shaheen is the Cray XC40 operated by Chaos Supercomputer Laboratory. In this study, we use a friction parameter that scales to a fracture or fault size. The fault or fractures are modeled as interfaces with rate and state characterizing by strong rate weakening at coseismic slip rate. The key parameter of this frictional model is the characteristic slip value called frictional state evolution distance, represented by capital L, or slip weakening distance as known as d sub c. Note that the fracture we consider is seismogenic, meaning that it can host a co-seismic slip if its fault or fracture size exceeds the nucleation size that is proportional to L. Or in other words, L has to scale down with decreasing fault or fracture size to support co-seismic slip. So how to infer the scaling relation of L to fracture size? We follow analytical solution relation of fracture energy and characteristic length L provided by Garagash 2021. We use the compilation of fracture energy data from Fiesca and Garagash 2050, plot with slip, with additional induced event as denoted by a colored symbol in this figure on the left. By using relation provided by Garagash 2021, we can translate the fracture energy into characteristic length L. Assuming the difference between friction at peak with weakened friction is close to 1 under effective normal stress. Assuming now the fracture or fault size is representative to source radius, one can find the scaling of L with even or fault fracture size. And then we use linear fit for scaling a relation L to the cell's radius. Note that we can establish the threshold of slip as a function of fracture energy, below which the assumed fracture model does not yield the solution for L, suggesting that other weakening mechanism may be involved, for example, thermal pressurization as presented by Vieska and Garagash 2015, where the original data comes from. The non-L solution is represented here by gray symbol on this figure B. To inspect the pre-stress condition on the manifold and fractures, we use the ratio of the potential stress drop to breakdown strength drop. And then this ratio can be used to see the optimally oriented fracture and fault. High value of R represent the optimally oriented fractures, and hence if perturbed, the fracture that corresponds to high R value will slip first. As you can see from the original model, the fractures are favorably oriented with homogeneous regional stress loading. However, it is difficult to see the overall fractures. And then, therefore, we systematically break down the original plot or original view, noted here as the exploding view, to see more details on every fractures. This plot will be used later on showing the result. For the exploding view on the right panel, you can see clearly which fractures that are optimally oriented and are also fractures that are not optimally oriented. It is worth to note that we use a constant dynamic and static friction coefficient, but varying only on a characteristic length L. Result of dynamic rupture scenario number 1. Let me remember you again. Scenario number 1 is injecting fluid into permeable fault core on the manifold. Here we use stress perturbation of 6 megapascal. Remember that the original fracture network is represented by this bottom left figure. The figure on the upper left shows the exploding view of the rupture time. Dark violet color denotes the earlier time, and blue to red color represent the later time. The red dot here illustrates the nucleation point on the rupture. So from the rupture time figure, you can already see how rupture evolves with time. And then on the right, you will see the evolution of slip velocity during cascading rupture in scenario number 1. Let me play the video. So rupture starts on the main fault plane, and then it propagates bilaterally left and right, and branches into neighboring fractures. Strong dynamic triggering occurs once the rupture on the main fault reaches the edge of a fault plane, especially on the left side of this main fault. As you notice, the cascading rupture occurs when the propagating rupture impedes the neighboring fractures. And then a result of dynamic rupture for scenario number 2. In this scenario, fluid injection injected into a volume of perturbing stress on the main fault distributed on the fracture network. Here we use stress perturbation of 4 megapascal. Let me remember you again. The original model is shown by this left bottom figure. Same as previous figure, the left panel, the left upper panel here represent the exploding view of rupture time. To better see what is going on, the video on the right will show you how the rupture evolves within the fracture network and does not trigger a runaway rupture on the main fault plane. Let me play the video. The rupture starts on the fractures, triggering the main fault plane, without triggering the main fault plane, and then it evolves to the connected neighboring fractures, creating a cascading rupture to the fracture network. Dynamic interactions among the fracture and the main fault plane initiates a rupture also on the main fault plane. However, the stress perturbation from dynamic interaction is still insufficient to generate a runaway rupture and only facilitates a self-arrested rupture, as you can clearly see here from the rupture time. Now in scenario number 3, where the scenario is similar to scenario number 4, the previous scenarios, but with stronger stress perturbation. Now from the exploding view of rupture time, we already can see an interesting rupture process on the main fault plane. Let me play the video. In scenario 3, the rupture starts on both main fault and a fracture network. Unlike scenario number 1, the main fault propagates unilaterally to the right, activating the neighboring fractures and initiates cascading rupture on the right side of the figure. And then the rupture on the main fault dies out. However, rupture on the interconnecting fracture is still going on. Interestingly, at t equal to 2.5 seconds, due to a dynamic interaction between fracture and the main fault plane, the main fault initiates, renucleate, and generating a runaway rupture. This runaway rupture also activates its neighboring fracture that are located on the left side of the main fault plane. Here. The summary of source property from all scenarios presented here can be shown in this table. 3 scenarios produce equivalent moment magnitude as well as seismic moment. The 3 scenarios generate sub-Rayleigh rupture speed. The overall speed, the overall slip on the scenario number 2 generates the least slip, which is about 12 centimeters. Scenario number 1 and number 3 have comparable average slip of about 17 centimeters. And then the average dynamic stress drop is about a 7 megapascal. However, the largest dynamic stress drop is in scenario number 3. The 3 scenarios have a very different moment tensor solution. Scenario number 1 and scenario number 3 produce a non-double couple moment tensor component. Surprisingly, a moment tensor in scenario number 2 produce a double couple moment tensor solution. From the distance, one can analyze the point source of moment rate function for this scenario. High moment rate occurs when the main fault starts to rupture, like in scenario number 1 and scenario number 3. Interestingly, in scenario number 3, the moment rate decays at t equal to 2.4 seconds. The renucleation on the main fault generates high moment rate function, but not as high as the scenario number 1, and then it dies out. To validate our simulation, if it is still plausible and realistic, we compare the property of cascading rupture to observation data. As you notice, the simulation of dynamic rupture scenario in this study is comparable to the observation data in terms of proportion of fracture energy with respect to the slip. And all scenarios in this study are represented by the gray symbols here. The key findings on this study can be listed into 3 key points. The fracture-oriented favorably to a regional stress loading connected fractures and close to critically stressed fracture host a cascading earthquake with or without runaway rupture on the main fault plane. A cascading rupture with and without a runaway rupture on the main fault produce different moment tensor solutions. Surprisingly, scenario number 2 results double couple moment tensor solutions. And then the cascading rupture in this study produced sub-Rayleigh rupture speed and plausible fracture energy in comparison to observation data. And then finally, we have ongoing work that explore the transition in a rupture mode from the rupture cascading over a fracture network to the rupture on the main fault plane only with a change in the regional stress orientation. So stay tuned with us. The reference of all presented materials in this presentation are listed below. Thank you for having us in this virtual EGU presentation.